Welcome back to Applied Physics. In this video, I want to talk about projectile motion. Projectile motion is, almost by definition, the idea of motion in two dimensions. Previously, we've studied motion in just one dimension, moving left and right where acceleration usually isn't a big factor, or moving up and down where you have to deal with the acceleration of gravity. A projectile is something that moves in two directions. This can be anything from, throwing a pencil to your friend across the room, throwing a baseball as a Major League Baseball pitcher, or launching a missile out of a cannon on a warship. The mathematics of all of these things behaves the same way, follows the same laws of motion. The most important of which is the law of isolation of motion. If we think about how this object is moving, we can break it into components. There is an x component of motion, which is just going to be motion along a straight line, and there's a y component of motion, where this object is going to go up and then back down, and that's also motion along a straight line. So if we look at each point of the motion and think about the position as a vector, think about the velocity as a vector, and think about the acceleration as a vector, then we can handle this using the exact same tools we've already dealt with. All right, let me get my head out of the way and let's dive right into an example. A baseball is thrown at 27 meters per second in an arc starting 35 degrees above the horizon. How far will it travel along the ground before it lands? The phrasing here might seem a little bit counterintuitive at first. How far will it travel along the ground? Well, it won't travel along the ground. It will travel in an arc through the air. But what we're really trying to get at there is which path are we measuring, right? The baseball is going to follow this parabolic trajectory. It's going to start over here, it's going to arc up, and it's going to fall back down. I don't want the distance of the arc. I don't want to calculate the distance along the arc. I'm asking for straight line distance from where it started to where it ended, measured along what I'm assuming is going to be level ground. So it's actually a simplifying assumption. Let's not worry about the extra distance it has to travel because it's going up and down. I just want to know how far away it is when it lands compared to where I am where I threw it. I'm also going to make a very important simplifying assumption here. And that assumption is that when the ball is released, it is released on the ground. That's an absolutely silly assumption, right? If I'm going to throw a baseball, I'm going to throw it with my hand somewhere in the vicinity of here. In the vicinity of here is in the vicinity of 6 feet, 2 meters above the ground. But that's not how I drew the picture, so that's not what we're going to do when we try to figure this out. All right, so let me get my head out of the way. Let's scroll this screen a little bit so we have some space to work. And let's start thinking about what's going to happen. Well, I've already explained that we want to break this thing into components. We are given an initial velocity. Our initial velocity is a vector. It is 27 meters per second. And I'm sorry, I was lazy when I copied that down. That should have been 27.0 meters per second. At 35 degrees. Right. Specifically, it says 35 degrees above the horizon. Well, that direction is the horizon. That direction is above the horizon. And if we sketch that out real quick, we can see that that is actually a way of describing an angle in standard position. So we don't have to worry about anything weird happening with our angle in this example. We also need to think about the acceleration. Well, the x component of the acceleration is going to be 0. It's not going to be accelerating left or right. And the y component of the acceleration is going to be the acceleration due to gravity, which is negative 9.80 meters per square second. I'm asked, how far is it going to travel? Well, I guess that's going to be s sub x. That's our unknown. And with just that information, it starts to feel like we're missing something, but we really aren't. In the x direction, we don't have to worry about acceleration. So we have the simple formula of kinematics. Movement in the x direction is equal to the velocity in the x direction times the time it has taken to travel. In the y direction, we do have acceleration, so we have a couple of formulas at our disposal. We know that Vfy is equal to V naught y plus at. We know that Sy is equal to V naught y times t plus 1/2 a, and this should be a y's t squared. And we know that V naught y squared plus V f y squared is equal to 2 times a times sy. These are all things that we have from our previous study, so we can just use these formulas no problem. That's a lot of formulas though, so let's see if we can break this down a little bit further. I'm going to go ahead and put a big circle here around s sub x to remind myself that's the thing I'm trying to figure out. The only equation it shows up in is this one, where I've got a Vx and I've got a t. All right, Vx is easy. Vx is going to be equal to V times the cosine of theta. V in this case is 27.0 meters per second. Theta in this case is 35 degrees. And my calculator is happy to tell me that 27.0 times the cosine of 35 is 22.1. That seems like it's going to be useful, so I'm going to go ahead and write that over here. Vx is equal to 22.1 meters per second. And while I haven't conclusively said it was going to be useful yet, while I'm at it, I might as well figure out the y component of the velocity as well. That's going to be v times the sine of theta. I'm running low on space, so I'm not going to write it out again, but 27.0 meters per second times the sine of 35 degrees. My calculator tells me that that is 15.5 meters per second. All right, so we've done a little bit of calculation. We've gotten a little bit further. Our goal is still to figure out s sub x. We have figured out v sub x. We still need to figure out t. So I'll go ahead and make a mark of that. T is unknown. So we definitely need an equation that involves t. This equation does not have t in it, so that's hopefully not going to be something we need. The other two equations do have t in them. All right, well, we've got Vy. I guess I should have been more careful on that because the velocity in the y direction does change, the velocity in the x direction does not. This is my initial velocity in the y direction, the velocity it was going when it was launched. So we've got that value, which does show up in both cases. We've got ay, which does show up in both cases. T shows up in both of these formulas. That's great to see. So then we're left with a question of, is the distance in the y direction or the velocity in the y direction more likely to be something we can figure out? Because we need one of them. It's very tempting. I always see when I give a problem like this, at least one student try to say, well, if it goes up and then back down, its final position in the y direction is the same as its initial position. Sy is equal to 0. Which is absolutely true, but not quite what we need here. It turns out if you try to plug that into the formula we have here, it's going to give you, oh yeah, so the time is 0. Because while it is true that at the end of the entire arc, the y position is going to be the same as where it is started, so the displacement in the y direction is 0, the formula is going to give you the first time that that time showed up, which is at the beginning. Because the initial position and the final position are the same, trying to work with position is actually a lot trickier than it seems. Instead, we need to make a different trick, and we've done this trick in one dimension already. There we go. The ball is going to go up, and then it's going to come back down. And it's probably a safe assumption that the path is going to be symmetric. The travel upward and the travel downward are going to look the same. So if we just figure out how long it takes to go up, and then double that, that will give us the total time it takes to go up and then back down. And going up is convenient, because if you throw a ball into the air, it is going to go upward, it's going to have an upward velocity, and then it's going to turn around and it's going to have a downward velocity. And the only way to go from an upward velocity to a downward velocity is for there to be that one instant at the top where the velocity becomes 0. That's what we need in order to be able to solve this problem. We need that Vf in the y direction is equal to 0. That will give us the time it takes from when it launches to when it hits the peak, which is not quite the time we need, but that's okay. We'll be able to get there. All right. Do I have everything I need? I think I have everything I need if I scroll down and give myself some space. So the formula I'm going to work with says that Vfy is equal to V naught y plus AT. And if I rearrange that, it gives me that t is equal to vfy minus v naught y all over a. Plugging in the values I have, vfy is 0, v naught y is 15.5 meters per second, and a is negative 9.80 meters per square second. Right, I guess I should be more careful, call that ay. There's only acceleration in the y direction. Physicists tend to be very lazy about that sort of thing, and I tend to be particularly lazy about that sort of thing, but that doesn't mean it's right. All right, so if I plug this into my calculator tells me that t is going to be 1.63. And if you look at the units there, you have meters per second divided by meters per square second. The meters cancel out, one of the seconds cancels out, and you'll be left with 1 over seconds, which is just seconds, which is exactly what we expect for a time. But remember that this time is time 1/2. It's the time to get from the launch point to the peak of the arc, and then we need to double that to get the time of 3.26 seconds for it to go up and then back down. This is the time, along with this velocity, that we can plug into our last formula. Sx is equal to Vx times t, 22.1 meters per second times 3.26 seconds. My calculator tells me that that is going to be 72.0 meters. All right, running out of space at the bottom of the page, but there we have it. It's a long way to go to get there. We had to solve a couple of different equations. We had to use 4 formulas, if you really think about it. Right? 2 of the formulas of kinematics. We had to use the formulas for finding the x and y components of a vector. And we also had to think about the physics of the fact that at the top of the arc, the ball is not moving up or down for 1 instant. And the physics of the arc upward and the arc downward are the same path. All right, so a lot going on in that problem. I've spent almost 20 minutes on this video trying to explain it. I think that's enough for one video. I'll wrap up here. Thanks as always for joining me, and I'll see you next time.